This session deals with coefficient of determination, that is R square, and this coefficient of determination is the measure of goodness of fit of a regression line. So after the estimation of parameters and the determination of the least square regression line, now we need to know how good is the fit of the regression line to the sample observations x and y. So we have already identified the regression line by estimating the values of beta 1 hat and beta 2 hat. And in this coefficient of determination, what we are doing is we are measuring the goodness of fit. That is, we are testing how good our fit or our regression line is to the actual population line or actual data. So the closer the observation to the line, the better the goodness of it. So the observations that we have identified, how far these observations are close to the regression line. So as much as closer means it is as good as possible. So that is the measurement, or that is the measurement that we have to do here in order to identify the goodness of it. So for that we are determining the R square value, which is termed as coefficient of determination. So here we will prove that a measure of goodness of fit is the square of correlation coefficient, that is R is the correlation coefficient, and square of this correlation coefficient, that is R square, it is measured in order to prove the goodness of fit. And this R square shows the percentage of total variation in y, that is the dependent variable, that can be explained by the independent variables x. So how far the change in y can be explained by the x's, which are the independent variables. So this is shown by the R square value. So for computing R square, so first we have to recall that our regression function, population regression function yi is equal to yi hat plus ui hat, or in the deviation form, mean deviation form, we can write this as small letter yi is equal to yi hat plus ui hat. So this is the equation in the mean deviation form, where yi is capital yi minus y bar, this is yi hat minus y bar. So when we are taking the deviation form, we are representing it with the small letter y and yi hat. Okay. Now as a next step, we can square the both sides and take summation over the sample. So let us sigma yi square is equal to sigma yi hat plus ui hat square. This is equal to, so here this can be considered as a plus b the whole square form. Okay, yi hat is the a, ui hat is b, so a plus b whole square. Then it can be written as sigma yi hat square a square plus sigma ui hat square, that is b square, plus 2 sigma yi hat ui hat, that is 2ab, a square plus b square plus 2ab. This will be equal to sigma yi hat square plus sigma ui hat square, and this component sigma yi hat ui hat will be equal to 0. So let us check this sigma yi hat ui hat, how this become 0. Okay, so consider this element, that is sigma yi hat ui hat is equal to yi hat. In the mean deviation form, we have proved yi hat value, it will be equal to beta 2 hat xi is the value for yi hat into ui hat is yi minus yi hat. Okay, so here sigma beta 2 hat xi into yi minus yi hat, again this yi hat can be written as beta 2 hat xi. This yi is also substituted with beta 2 hat xi. Okay, now let us just open the bracket. It will become beta 2 hat sigma xi yi minus beta 2 hat square sigma xi square. So here beta 2 hat xi into yi into sigma beta 2 hat sigma xi yi, again beta 2 hat so beta 2 hat square xi square into sigma. This will be equal to beta 2 hat into, we can take beta 2 hat as common, sigma xi yi minus beta 2 hat sigma xi square. So beta 2 hat is taken as common, so this is sigma xi yi minus beta 2 hat into sigma xi y. One beta 2 hat is taken outside. This is equal to beta 2 hat into sigma xi yi minus, again when we are estimating the values for beta 2 hat, we have derived one equation for beta 2 hat as sigma xi yi by sigma xi square. Hope you remember this equation when we are doing the estimation. So alternative equation for beta 2 hat, that is sigma xi yi by sigma xi square into sigma xi square. Now we can cut this to, again sigma xi yi minus sigma xi yi, this will be equal to beta 2 hat into 0. So overall this element will become 0. So here 2ab, in this 2ab sigma yi hat ui hat is 0. We have proved this. Therefore we can write our equation as sigma yi square is equal to sigma yi hat square plus sigma ui hat square. That is sigma yi square is equal to sigma yi hat square plus sigma ui hat square. Okay, this can also be represented as sigma yi square is equal to beta 2 hat square sigma xi square plus sigma ui hat square. What is this? Just we have substituted the value of yi hat as beta 2 hat sigma xi square. Now let this equation be the first equation and this be the second equation. This first equation can be seen as a sum of squares or sum of square equations. Various sum of squares are appearing in this equation. So that is our first equation, sigma yi square is equal to sigma yi hat square plus sigma ui hat square. So in this equation all the elements are represented in sum and square form. So sum of square form. First is sigma yi square. This is the represented as total sum of squares, sigma yi square. That is, this is equal to sigma yi minus y bar, right? Mean deviation form. So sigma yi minus y bar square. This is the total sum of square. That means total variation of actual y about the sample mean. So this is the actual y, this is the mean value. So variation of this actual y from the mean value is represented here and it is called total sum of squares. Now sigma yi hat square is sigma yi hat minus y bar whole square. It is called explained sum of square or ESS. Okay, so this is represented as variation of the estimated y value about the mean value. Yi hat is the estimated y value. This is the mean value. So variation of estimated y value from the mean value is represented as sigma yi hat square. This can be again rewritten as sigma yi hat square is equal to beta 2 hat square sigma xi square, because for yi hat we have identified the equation yi hat is equal to beta 2 hat xi. This is the equation in mean deviation form. So substituting this value here, we will get beta 2 hat square sigma xi square. So this is the explained sum of square, and this third component sigma ui hat square is called residual sum of square. So ui hat is nothing but the error term or the residual term or unexplained variation of y, that is ui hat. So this sigma ui hat square represents the unexplained variation of y values about the regression line. So the unexplained part or the omitted part is shown in sigma ui hat square. So it is called residual sum of square. So let us write these equations as total sum of square is equal to explained sum of square plus residual sum of square. So that means various sum of squares are explained here: total sum, explained sum, and residual sum of squares. So this total variation in observed y, that is total sum of square, can be divided into two components: explained sum of square and residual sum of square. So there are two parts, that is one is attributed to the regression line, that is explained sum of square, and the other is the random factor. Now let us represent this equation diagrammatically. This is x, this is y. Now this is the sample regression function or our regression line. It is represented as beta 1 hat plus beta 2 hat xi. So this is our regression line. Now here we have to find the mean values. Y bar, and that this is x bar mean value. Okay. Okay. Now this is the yi hat value. So that is the estimated value yi hat. That is the point in the regression line. That is the estimated y value yi hat. Now this is the actual y value, and this is the point x bar y bar mean value. Okay, so what is total sum of square? That is yi minus y bar. Okay, so yi y bar, so this area is the yi value, that is yi minus y bar. Now what is explained sum of square? That is yi hat minus y bar. So yi hat and y bar, so this is the small letter yi hat, that is yi hat minus y bar. Now what is residual sum of square? That is sigma ui hat square, which is the difference between yi and yi hat. So this is the ui hat, that is yi minus yi hat. Difference between actual value and estimated value will show the error term. So this is the total sum of square. Okay, so this is the total sum of square. Now small letter yi hat is explained sum of square, and ui hat, it is the residual sum of square. So this total sum of square is ESS plus RSS. So that this equation is represented in this figure. Now again let us continue with the equation, that is TSS equal to ESS plus RSS. Okay, now dividing throughout with TSS, dividing the whole equation with TSS, it will become TSS by TSS equal to ESS by TSS plus RSS by TSS. So we have divided the whole equation with TSS. This will become 1 equal to ESS by TSS plus RSS by TSS, or this can be written as sigma yi hat square divided by sigma yi square plus sigma ui hat square divided by sigma yi square, or it can also be written as sigma capital yi minus y bar whole square, yi hat minus y bar the whole square divided by capital yi minus y bar whole square plus sigma ui hat square divided by sigma yi minus y bar the whole square. So these are different forms or different expansions of the equation. Now we can define our r square is equal to sigma yi hat minus y bar the whole square divided by sigma yi minus y bar the whole square, or this is nothing but sigma yi hat square divided by sigma yi square, or it is our ESS divided by TSS. So this is the definition for r square value, which is the ratio of explained sum of square to total sum of square. So the quantity defined by ESS by dividing explained sum of square with the total sum of square is called coefficient of determination r square, and this r square value is the commonly used measure of goodness of fit of any regression line. So verbally this r square measures the proportion or percentage change of total variation in y explained by the regression model, that is ESS. So ratio of explained sum of square to total sum of square is the r square value, which measures the goodness of fit of regression line. Okay. So thus we derive the value or the equation for r square. It is nothing but ESS by TSS, or sigma yi hat square divided by sigma yi square. So we can also write r square as r square is equal to ESS by TSS, or 1 minus RSS by TSS. Since in the previous case when we divide the whole term with TSS, we got this equation 1 is equal to, okay, now here this is the r square value, therefore 1 minus RSS by TSS is the r square value. So r square can also be represented as 1 minus RSS by TSS. Okay, so this is the r square value, and we can bring some properties, or we can define some properties of r square. Properties of r square. These properties is considered while we are measuring the goodness of it. So first property is that r square is a non-negative quantity. Okay, non-negative quantity. Simply it is because this is a square term. So whatever is the value of r, the square term will give a positive value. So always the r square is a non-negative quantity. And second property is that the limit of r square is 0 and 1. That is, r square lies between 0 and 1. So there is two extremes, that is r square equal to 1 and r square equal to 0. So r square equal to 1 means our regression line is a perfect fit. So if r square value is 1, that is our regression line is a perfect fit, that is our yi hat will be equal to yi. Our actual value and the estimated value will become equal. That is our regression line, actual regression line will be equal to the estimated regression line, and our estimated regression line will be the perfect fit. On the other hand, r square equal to 0 implies there is no relationship between the regressant and the regressor. So r square equal to 0 means no relation between regressant and regressor, that is our beta 2 hat will be equal to 0. There is no relation between regressant and regressor, or the x values and the dependent variable y. So these are the properties of r square. So from the value of r square we can determine whether our regression line is closer to 1 or closer to 0. Closer to 1 means the regression line is becoming perfect fit. Closer to 0 means there is no relation between the regressant and the regressor. So this is all about coefficient of determination r square, which is the measure of goodness of fit. Thank you.